On February 11, 2017, at California's Oroville Dam, spillway gates operated precisely as designed. Water discharged at controlled rates through engineered channels built to withstand calculated hydraulic forces. Flow velocities matched design specifications. Concrete aprons distributed energy loads according to engineering principles established decades earlier. The spillway performed its primary function, moving water safely from reservoir to river. Yet within hours, evacuation orders would force 180,000 residents from their homes. The threat emerged not from dam failure, but from the spillway system itself, specifically from processes occurring beneath the concrete surface where water had found pathways that engineering calculations had not anticipated. The Oroville spillway had been constructed according to standard practices, concrete slabs placed over prepared bedrock, with drainage systems designed to relieve uplift pressures. These design assumptions, that subsurface drainage would remain functional, that bedrock preparation would prevent infiltration, that hydraulic forces would remain confined to surface channels, had governed construction decisions and operational protocols for 50 years. But spillway concrete, like all infrastructure, ages. Joints develop microscopic separations. Drainage systems accumulate sediment. Water, under pressure and given sufficient time, exploits every available pathway. When spillway discharge reached levels not seen since construction, water behavior departed from the controlled, surface flow that designers had modeled. The evacuation was ordered not because the dam would fail, but because water had begun rewriting the rules that governed spillway performance. How does infrastructure designed to prevent disaster become the mechanism that triggers it? The Oroville Dam spillway system emerged from a specific engineering philosophy that dominated American dam construction in the 1960s. Flood control through massive concrete structures that could safely channel extreme water volumes while maintaining reservoir operations. When California's Department of Water Resources began designing what would become the world's tallest dam in 1957, the spillway represented the critical interface between controlled storage and uncontrolled discharge, a concrete pathway that would allow operators to prevent catastrophic overtopping by releasing water at rates up to 270,000 cubic feet per second. The spillway's design reflected established Bureau of Reclamation principles that had governed major dam construction since the 1930s. Water would enter through radial gates controlled from a service bridge, flow down a concrete-lined chute inclined at carefully calculated angles, and dissipate energy in a stilling basin before rejoining the Feather River. This approach assumed that concrete, properly placed over prepared bedrock, would contain hydraulic forces indefinitely. The design premise was straightforward. Water would remain on the surface of the spillway, following predetermined flow paths, with any uplift pressures safely relieved through engineered drainage systems embedded within the concrete structure. The spillway chute itself extended 3,000 feet from the dam's outlet structure to the river below, dropping 730 feet in elevation. Engineering calculations determined that the chute required a specific concrete thickness, typically 12 to 18 inches, over a foundation of carefully prepared rock. The bedrock beneath the spillway consisted of what geologists in the 1950s classified as metavolcanic rock, later redesignated as the Smartville ophiolite, a formation of weathered volcanic material that had undergone significant chemical alteration over geological time. Critical to the spillway's function was an extensive drainage system designed to prevent water from accumulating beneath the concrete slabs. Herringbone patterns of terracotta drain pipes were embedded within the spillway structure, positioned just 5 to 6 inches below the concrete surface. These drains served a dual purpose. They prevented uplift pressures from developing under the concrete during spillway operation, and they provided a pathway for any water that might penetrate the concrete surface to exit safely without compromising structural integrity. The design assumed several conditions that would prove critical to understanding the 2017 failure. First, engineers expected that the concrete-to-bedrock interface would remain watertight, preventing significant subsurface water infiltration. Second, the embedded drainage system was expected to function indefinitely, providing reliable pressure relief throughout the spillway's operational life. Third, the underlying bedrock was assumed to be sufficiently competent to support the concrete structure without degradation, despite geological evidence indicating the presence of weathered rock layers, or saprolite, in the spillway foundation area. Spillway operations were governed by precise hydraulic calculations that determined safe discharge rates based on reservoir levels and downstream channel capacity. Operators relied on established protocols that prioritized gradual water releases to prevent sudden flow increases that might damage downstream infrastructure or endanger river communities. The spillway gates could be operated individually or in combination, allowing operators to fine-tune discharge rates based on hydrologic conditions and flood control requirements. The operational philosophy emphasized predictability and control. Spillway flows were expected to behave according to well-understood hydraulic principles, with water velocities, depths, and energy dissipation occurring within calculated parameters. This predictability was essential for safe operation, as spillway discharge directly affected river levels, power generation at downstream facilities, and flood protection for communities throughout the Feather River Basin. During normal operations, the spillway remained dry except during flood control releases or scheduled maintenance flows. This design choice reflected standard practice for flood control spillways, where structures remained inactive for extended periods between high water events. The assumption was that concrete structures could withstand both wet-dry cycling and the thermal stresses associated with intermittent use without significant degradation. The spillway's auxiliary components included a separate emergency spillway, designed to operate only during extreme flood events when the main spillway reached capacity. This ungated structure consisted of a concrete weir that would allow water to flow over natural hillside terrain in a controlled manner. The emergency spillway represented a backup system, designed to prevent dam overtopping by providing an additional discharge pathway that could handle flows exceeding the main spillway's design capacity. Instrumentation for monitoring spillway performance focused primarily on hydraulic parameters, flow rates, water levels, and gate positions. The system included limited provisions for monitoring the structural condition of the spillway chute itself. This instrumentation philosophy reflected the prevailing assumption that properly constructed concrete would perform reliably for the structure's design life without requiring continuous structural monitoring. The spillway design incorporated safety factors intended to accommodate uncertainties in hydraulic loading, concrete performance, and foundation conditions. These factors were based on engineering judgment and experience with similar structures, rather than on comprehensive testing of the specific materials and conditions at Oroville. The safety margins were considered adequate for the range of operating conditions anticipated during the spillway's design life. However, the design process occurred before modern understanding of several critical factors that would later prove relevant to spillway performance. In the 1960s, engineers had limited knowledge of alkali aggregate reactions in concrete, the long-term effects of wet-dry cycling on concrete durability, and the behavior of drainage systems subjected to decades of sediment infiltration. The design also preceded current understanding of how weathered volcanic rocks respond to sustained hydraulic loading and thermal cycling. The spillway's construction occurred between 1965 and 1968, during a period of unprecedented dam building activity in California. Quality control procedures followed established practices, with periodic testing of concrete strength and inspection of reinforcement placement. However, construction documentation from this period reveals limited attention to the long-term performance of embedded drainage systems or the detailed characterization of foundation rock properties below the prepared surface. The completed spillway represented state-of-the-art flood control engineering for its time, incorporating established design principles and construction techniques that had proven successful at numerous other facilities. The structure met all applicable design standards and regulatory requirements, with approval from multiple engineering review boards and consulting panels assembled specifically for the Oroville project. This design framework created the operational environment that would govern spillway performance for nearly 5 decades. Operators would make decisions based on hydraulic calculations that assumed structural integrity, while structural engineers would evaluate performance based on hydraulic loading assumptions that assumed predictable flow characteristics. The spillway system represented a carefully balanced engineering solution that depended on the continued validity of fundamental assumptions about concrete durability, foundation stability, and drainage system performance. The implications of these design assumptions would not become apparent until February 2017, when prolonged spillway operation under conditions not encountered since the structure's completion would reveal the gap between design intent and physical reality. The spillway had been designed to handle water. It had not been designed to reveal what time, weather, and accumulated wear had done to the hidden infrastructure that made safe water handling possible. The spillway system that operators inherited in 1968 contained vulnerabilities that would remain hidden for decades, embedded within design choices and maintenance practices that appeared entirely reasonable at the time of implementation. These latent conditions did not represent failures of engineering judgment, but rather the inevitable accumulation of small compromises and unexamined assumptions that would eventually align to create pathways for catastrophic failure. The most significant latent condition involved the spillway's drainage system, which had been installed during construction with terracotta pipes positioned just inches below the concrete surface. These pipes, arranged in herringbone patterns throughout the chute, were designed to intercept any water that might penetrate the concrete and channel it safely away from the structure. However, the drainage system's effectiveness depended on maintaining clear flow paths over operational timeframes that exceeded the experience base of any existing spillway. By the 1980s, routine inspections began documenting evidence of drainage system degradation. Sediment infiltration had partially blocked some drain outlets, reducing the system's capacity to relieve uplift pressures. More concerning, chemical analysis revealed that some terracotta pipes were experiencing material degradation due to prolonged exposure to alkaline conditions created by concrete chemistry. The pipes were slowly dissolving, creating void spaces within the spillway structure that operators could not directly observe. This drainage system deterioration created a hidden vulnerability that contradicted fundamental design assumptions. Engineers had calculated spillway safety factors based on the assumption that uplift pressures would be reliably relieved through functional drainage. As drainage capacity decreased, the actual safety margins were being eroded in ways that could not be detected through surface inspection or standard hydraulic monitoring. Maintenance procedures during the spillway's operational life focused primarily on concrete surface repairs and gate mechanism servicing. These activities followed established protocols for dam maintenance, emphasizing visible components and mechanical systems that could be tested and verified. However, the embedded drainage system lay beyond the reach of routine maintenance, accessible only through expensive and disruptive excavation that was never authorized during the spillway's first 4 decades of operation. The maintenance philosophy reflected broader organizational assumptions about concrete infrastructure durability. Concrete structures were expected to provide decades of reliable service with minimal intervention, a belief supported by experience with other major dams constructed during the same period. This confidence in concrete permanence discouraged intensive investigation of subsurface conditions, particularly when surface inspections revealed no obvious signs of distress. Organizational factors within the California Department of Water Resources further contributed to the accumulation of latent conditions. Budget constraints during the 1980s and 1990s led to deferral of comprehensive structural assessments that might have revealed drainage system problems earlier. Engineering staff turnover meant that institutional knowledge about construction details and early operational experience was gradually lost, replaced by procedural compliance that emphasized routine inspections over fundamental system evaluation. The regulatory environment also shaped maintenance priorities in ways that inadvertently masked emerging problems. Federal guidelines for dam safety focused primarily on structural stability and flood control performance, with less emphasis on the detailed condition of auxiliary systems like spillway drainage. Compliance inspections verified that the spillway could discharge required flow volumes and that concrete surfaces showed no obvious cracking, but they did not mandate investigation of subsurface infrastructure condition. Training protocols for spillway operators emphasized hydraulic control and flood management procedures, with limited attention to recognizing early signs of structural deterioration. Operators learned to monitor water levels, gate positions, and discharge rates, but they received minimal guidance on identifying conditions that might indicate underlying structural problems. This training approach reflected the design assumption that structural components would remain stable throughout the spillway's operational life. The spillway's instrumentation system compounded these organizational limitations by providing extensive data on hydraulic performance while offering minimal information about structural condition. Operators could precisely monitor flow rates and water pressures, but they had no direct means of assessing the integrity of the drainage system or the condition of the concrete bedrock interface. This instrumentation bias reinforced the operational focus on hydraulic control while maintaining structural assumptions that were becoming increasingly questionable. Documentation practices during routine maintenance activities inadvertently obscured evidence of emerging problems. Work orders typically focused on specific repair tasks rather than comprehensive condition assessment, creating records that captured individual symptoms without revealing systematic deterioration patterns. When maintenance crews repaired surface cracks or replaced concrete sections, these activities were documented as routine improvements rather than responses to underlying structural changes. The spillway's design had also created a maintenance trap through its herringbone drainage system configuration. The intricate network of buried pipes made comprehensive inspection extremely difficult, while the system's distributed nature meant that partial blockages might not significantly affect overall spillway performance until deterioration became widespread. Operators could not easily distinguish between normal operational variations and the gradual degradation of critical subsurface infrastructure. Seasonal operation patterns further masked the progression of structural deterioration. The spillway operated primarily during winter flood seasons, remaining dry for extended periods between high water events. This intermittent use pattern meant that emerging problems might not become apparent until spillway discharge reached levels that had not been sustained for years or decades. The wet-dry cycling also created thermal and chemical stresses that accelerated material degradation in ways that were poorly understood when the spillway was designed. Professional culture within the dam engineering community contributed to delayed recognition of spillway vulnerabilities. Engineers naturally focused on demonstrated performance rather than speculative failure modes, particularly when structures had operated successfully for decades. The spillway's reliable flood control performance during major storms in the 1980s and 1990s reinforced confidence in the design approach, discouraging investigation of theoretical problems that had no obvious operational impact. The accumulation of these latent conditions created a situation where the spillway's apparent reliability masked fundamental changes in its structural behavior. Surface inspections continued to show acceptable concrete condition, hydraulic performance remained within design parameters, and flood control operations proceeded according to established procedures. However, the hidden infrastructure that made this performance possible was gradually failing in ways that would not become apparent until extreme operating conditions exposed the accumulated degradation. By 2017, nearly 50 years after construction, the spillway represented a complex system where original design assumptions no longer accurately reflected physical reality. The drainage system that was supposed to prevent uplift pressures had been compromised by decades of sediment infiltration and material degradation. The bedrock foundation that was expected to provide stable support had been altered by prolonged exposure to water infiltration and thermal cycling. The concrete structure that appeared sound from surface inspection was underlain by void spaces and weakened interfaces that contradicted engineering calculations. These latent conditions had not triggered any obvious warning signs that would have prompted immediate corrective action. The spillway continued to perform its primary function of discharging flood flows, and routine inspections found no evidence of imminent failure. The hidden deterioration was only detectable through comprehensive subsurface investigation that had never been undertaken, due to cost considerations and confidence in the original design. The stage was set for a failure mode that would combine hydraulic forces with structural vulnerabilities in ways that the original design had not anticipated. When sustained spillway operation finally occurred in February 2017, the accumulated effects of decades of hidden deterioration would interact with hydraulic loading to create conditions that overwhelmed the spillway's compromised structural capacity. The winter of 2016 to 2017 brought California unprecedented rainfall following years of severe drought. By late January 2017, Oroville Reservoir had risen from critically low levels to near capacity, forcing operators to begin sustained spillway releases for the first time since 1997. What appeared to be routine flood control operation would reveal the accumulated effects of decades of hidden infrastructure degradation. On February 6, 2017, spillway operators began controlled releases at approximately 25,000 cubic feet per second to manage rising reservoir levels. Flow rates remained well within design parameters, and hydraulic conditions appeared entirely normal. Water entered through the radial gates, accelerated down the concrete chute, and dissipated energy in the stilling basin exactly as engineering calculations predicted. Surface observations revealed no unusual conditions, and operators had no reason to suspect that anything other than routine flood control was occurring. However, beneath the spillway's concrete surface, conditions were departing significantly from design assumptions. The sustained flow was creating hydraulic pressures that the compromised drainage system could no longer adequately relieve. Water began infiltrating through concrete joints and microcracks that had developed over decades of thermal cycling and chemical exposure. This infiltration process was invisible to operators, who had no instrumentation capable of detecting subsurface water accumulation. The infiltrating water encountered foundation conditions that differed substantially from what engineers had assumed during design. Instead of competent bedrock capable of supporting the concrete structure indefinitely, the water reached layers of saprolite, weathered volcanic rock that had been chemically altered by geological processes over millions of years. This material, which appeared stable when dry, became highly erodible when saturated and subjected to hydraulic pressure. For several days, spillway operation continued without obvious incident. Operators maintained discharge rates according to established flood control protocols, responding to rising reservoir levels by gradually increasing flow through additional gate openings. The spillway appeared to perform exactly as designed, handling increasing water volumes while maintaining controlled downstream releases. Hydraulic monitoring showed flow rates, velocities, and energy dissipation occurring within expected parameters. The divergence between apparent performance and actual structural condition became critical on February 7, when operators increased spillway discharge to approximately 52,000 cubic feet per second. This flow rate, while still well below the spillway's design capacity, created hydraulic conditions that had not been sustained since the structure's completion in 1968. The increased discharge generated higher pressures throughout the spillway system, including uplift pressures beneath the concrete that the degraded drainage system could not adequately manage. At approximately 9:30 a.m. on February 7, a spillway inspector conducting routine visual surveillance noticed what appeared to be unusual water flow emerging from the concrete surface near the spillway's midsection. Initial observations suggested possible concrete joint separation, a minor maintenance issue that would normally require investigation but not immediate operational response. The inspector reported the observation to operations staff, initiating a standard protocol for investigating potential spillway anomalies. What operators could not see was that water infiltration had reached a critical threshold where hydraulic pressure exceeded the structural capacity of the weakened foundation interface. Beneath the concrete, erosion had begun removing saprolite material, creating void spaces that undermined structural support. The visible water emergence represented overflow from a much larger subsurface erosion process that was rapidly expanding beyond the reach of surface observation. Operations staff initially attempted to assess the situation using standard visual inspection procedures, examining the spillway surface for obvious signs of structural distress. These inspections, conducted while water continued flowing at 52,000 cubic feet per second, revealed concrete surface irregularities but provided no direct information about subsurface conditions. The limitation of surface-based assessment became apparent as operators tried to evaluate whether continued spillway operation posed immediate safety risks. The critical decision point occurred when operations managers faced a fundamental choice: continue spillway operation to maintain reservoir control, or shut down the spillway to investigate the observed anomaly. This decision required evaluating competing risks with limited information about actual spillway condition. Continuing operation might worsen whatever structural problem was developing, but shutting down the spillway would force reservoir levels higher, potentially requiring use of the untested emergency spillway. At 11:55 a.m. on February 7th, operators made the decision to shut down the main spillway to allow detailed inspection of the observed anomaly. This decision reflected prudent caution based on available information, but it also initiated a sequence of events that would reveal the full extent of infrastructure deterioration. When spillway flow ceased, the true scale of subsurface erosion became visible for the first time. The sudden cessation of water flow exposed a massive crater where concrete had been undermined and foundation material had been eroded away. The crater extended approximately 300 feet in length and 170 feet in width, reaching depths of up to 40 feet below the original spillway surface. The scale of the erosion indicated that subsurface deterioration had been progressing for some time before becoming visible, hidden by the flowing water that had masked the developing cavity. More alarming was the discovery that the erosion had extended well beyond the concrete spillway structure itself, penetrating deep into the hillside that supported the spillway chute. The eroded material included not only saprolite foundation layers, but also structural fill that had been placed during original construction. This extensive erosion suggested that the spillway's structural integrity had been fundamentally compromised in ways that could not be quickly repaired. The crater's configuration revealed the mechanism of failure with stark clarity. Water infiltration through degraded concrete joints had reached the saprolite foundation, where sustained hydraulic pressure had initiated progressive erosion. The compromised drainage system had been unable to intercept this infiltration, allowing water to accumulate at the concrete bedrock interface where it generated uplift pressures that exceeded structural capacity. Once erosion began, the flowing water accelerated the process by removing material and creating increasingly large void spaces beneath the concrete. Inspection of the exposed crater also revealed evidence that the failure process had been developing gradually, rather than occurring suddenly. Multiple layers of eroded material showed distinct stages of deterioration, indicating that foundation erosion had been progressing through successive wet seasons without detection. The final catastrophic exposure represented the culmination of a process that had been undermining spillway integrity for an extended period. The implications of this discovery extended far beyond the immediate structural damage. The spillway failure had occurred during relatively modest flood conditions, at flow rates representing only a fraction of the structure's design capacity. This suggested that the spillway's actual structural capacity had been reduced far below design assumptions through the accumulated effects of infrastructure degradation. More critically, the failure had developed without triggering any of the monitoring systems or visual indicators that operators relied upon to assess spillway condition. Operations staff now confronted a situation that had not been anticipated in any emergency procedure. The main spillway was structurally compromised and could not safely operate, but reservoir levels continued rising due to ongoing storm inflows. The emergency spillway, which had never been used and was not designed for sustained operation, represented the only remaining option for reservoir control. However, activating the emergency spillway would create new risks, as this auxiliary system had its own limitations and potential failure modes. The divergence between operator expectations and physical reality was now complete. The spillway that had appeared to function normally just hours earlier was revealed to be structurally compromised beyond immediate repair. The infrastructure that operators had trusted to provide reliable flood control had been silently degrading for years, maintaining an appearance of competence while losing the capacity to perform safely under sustained loading. The failure exposed not just physical deterioration, but the inadequacy of inspection and monitoring systems that had failed to detect the progressive loss of structural integrity. The massive crater exposed by the spillway shutdown revealed a failure mechanism that contradicted fundamental engineering assumptions about concrete infrastructure behavior. The erosion pattern provided forensic evidence of how water infiltration, foundation deterioration, and structural uplift had combined to create catastrophic undermining that remained invisible until the moment of exposure. Understanding this failure chain required reconstructing the physics of progressive deterioration that had been developing beneath the spillway surface for decades. The failure originated at the interface between concrete and bedrock, where design assumptions about waterproof bonding had proven incorrect over operational timeframes. concrete placement during the 1960s had followed standard procedures for achieving adhesion to prepared rock surfaces, but these procedures did not account for the long-term effects of thermal cycling, chemical exposure, and micro-movement that gradually compromised the bond integrity. Seasonal temperature variations caused differential expansion between concrete and rock, creating microscopic separations that allowed water infiltration during subsequent spillway operations. This infiltration process accelerated during periods of sustained spillway discharge, when hydraulic pressure forced water into any available pathway through the concrete structure. The compromised drainage system, originally designed to intercept such infiltration, had been rendered ineffective by decades of sediment accumulation and terracotta pipe deterioration. Instead of being safely channeled away, infiltrating water accumulated at the concrete-rock interface where it generated uplift pressures that the original design had assumed would never occur. The bedrock beneath the spillway consisted of saprolite, developed from the Smartville ophiolite, a geological formation that exhibited dramatically different properties when saturated compared to its dry state. During design and construction, this material had appeared competent and stable, supporting engineering confidence in long-term foundation performance. However, when subjected to sustained hydraulic pressure from accumulated infiltration, the saprolite became highly erodible, losing structural integrity through chemical dissolution and particle transport. The erosion mechanism followed a predictable progression once critical conditions were established. Water infiltration created hydraulic pressure at the concrete saprolite interface, initially causing minor material displacement in the most chemically altered zones. As small amounts of saprolite were removed, the resulting void spaces allowed greater water accumulation, which increased hydraulic pressure and accelerated erosion rates. This positive feedback process continued beneath the concrete surface, creating progressively larger cavities that undermined structural support. The concrete structure above this developing erosion initially maintained its structural integrity through beam action, spanning across void spaces without obvious surface distress. However, as erosion expanded both laterally and vertically, the unsupported concrete spans exceeded their structural capacity. The final crater formation occurred when concrete slabs, no longer adequately supported by underlying foundation, collapsed into the eroded cavity beneath. Forensic analysis of the exposed crater revealed multiple generations of erosion activity, indicating that the failure process had been episodic rather than continuous. Different layers of eroded material showed distinct characteristics corresponding to various spillway operations over the structure's operational history. Earlier erosion events had removed chemically altered saprolite, while more recent activity had penetrated deeper into more competent rock layers as hydraulic pressure increased with accumulated void volume. The crater's asymmetric configuration provided additional evidence of how water flow patterns had influenced erosion development. The upstream end of the crater showed deeper excavation where hydraulic pressure was highest, while the downstream extent followed natural drainage patterns in the underlying rock structure. This erosion pattern confirmed that subsurface water movement had been controlled by geological features that were not fully characterized during original design investigations. Measurement of the eroded volume revealed the scale of material removal that had occurred without detection. Approximately 1.5 million cubic feet of foundation material had been removed from beneath the spillway structure, creating void spaces that extended up to 180 feet beyond the original concrete edges. This massive erosion had progressed through multiple spillway operations without triggering any monitoring system or visual indicator that might have warned operators of developing structural compromise. The timing of final crater exposure corresponded with hydraulic conditions that exceeded a critical threshold for continued concrete structural integrity. When spillway discharge reached 52,000 cubic feet per second on February 7, the combination of increased hydraulic pressure and reduced foundation support created conditions where the remaining concrete structure could no longer maintain stability. The visible water emergence that prompted operator concern represented the point where internal hydraulic pressure overcame the concrete's capacity to contain subsurface flow. Temperature measurements taken after crater exposure revealed additional evidence of the failure mechanism. Thermal imaging showed that water temperatures in the eroded cavity were several degrees warmer than spillway surface flow, indicating that the subsurface water had been in contact with the foundation for extended periods. This thermal signature supported the conclusion that water infiltration and accumulation had been occurring long before the final structural failure. Chemical analysis of water samples from the crater provided further forensic evidence of progressive foundation deterioration. Dissolved mineral content significantly exceeded levels typical of surface spillway flow, confirming extensive chemical interaction between infiltrating water and saprolite foundation materials. The specific mineral composition indicated that chemical dissolution had been occurring over time frames consistent with years rather than days of water-rock contact. The failure mechanism also explained why routine spillway inspections had failed to detect developing problems. Surface-based visual inspection could not penetrate the concrete structure to assess subsurface conditions, while the spillway's hydraulic performance remained within acceptable parameters despite progressive foundation erosion. The structural deterioration had been occurring in a zone that was inaccessible to conventional monitoring techniques and had not yet affected the spillway's primary function of discharging water. Structural calculations performed after crater exposure revealed how dramatically the spillway's load-carrying capacity had been reduced by foundation erosion. The concrete slabs that had appeared structurally adequate when assumed to be fully supported were actually operating far beyond their design limits as they spanned across growing void spaces. The factor of safety that engineers had incorporated into the original design had been completely eliminated by foundation deterioration that was not anticipated in design calculations. The physics of the failure also demonstrated why the erosion process had accelerated rather than stabilizing over time. Unlike surface erosion, which typically reaches equilibrium as resistant materials are exposed, the subsurface erosion at Oroville had encountered progressively more vulnerable foundation conditions as it penetrated deeper into chemically altered rock layers. Each erosion cycle had created conditions that facilitated more extensive deterioration during subsequent spillway operations. Analysis of spillway flow conditions during the failure development revealed another critical factor. The sustained discharge rates that triggered final failure were not extreme by historical standards, but they represented the longest continuous operation at moderate flow rates in the spillway's operational history. Previous spillway operations had typically involved higher peak flows for shorter durations, which had not provided sufficient time for the progressive hydraulic pressure accumulation that ultimately caused foundation failure. The crater formation marked the point of no return for spillway structural integrity. Once the foundation erosion was exposed to atmospheric conditions and direct spillway flow, any attempt to resume normal operation would accelerate erosion at rates that could undermine adjacent structures, including the spillway gates and approach channel. The physical evidence revealed that the spillway's capacity for safe flood control had been permanently eliminated by the accumulated effects of infrastructure deterioration that had remained hidden for decades. The failure chain demonstrated how multiple design assumptions could be invalidated simultaneously without producing obvious warning signs. The assumption of permanent concrete bedrock bonding, the assumption of effective drainage system performance, and the assumption of competent foundation materials had all proven incorrect. But their combined failure had remained undetectable until catastrophic exposure occurred. The spillway had continued to function hydraulically even as it lost the structural capacity necessary for safe long-term operation. With the main spillway rendered inoperable by catastrophic foundation failure, operators confronted an unprecedented scenario that had not been anticipated in any emergency procedure: rising reservoir levels with no reliable means of controlled discharge. The emergency spillway, which had never been used in 50 years of dam operation, represented the only remaining option for preventing reservoir overtopping, but activating this auxiliary system would create new risks that were poorly understood and potentially more dangerous than the original spillway failure. The emergency spillway consisted of an ungated concrete weir designed to allow automatic overflow when reservoir levels reached elevation 901 feet, approximately 50 feet below the dam's crest. Unlike the main spillway's controlled gate system, The emergency spillway operated as a simple overflow structure with no mechanism for regulating discharge rates. Water would flow over the weir, down an unlined natural hillside, and eventually reach the Feather River through an erosion-prone channel that had never been subjected to sustained high-velocity flow. As reservoir levels continued rising due to ongoing storm inflows, operators calculated that emergency spillway activation would occur within 24 to 48 hours unless alternative discharge methods could be implemented. Attempts to temporarily repair the main spillway were quickly abandoned when engineering assessment revealed that the foundation erosion extended far beyond what could be addressed through emergency measures. The crater's depth and lateral extent indicated that any concrete placement would lack adequate structural support and could fail catastrophically under renewed spillway operation. On February 11, 2017, at approximately 8:00 a.m., Lake Oroville reached elevation 901 feet, triggering automatic overflow through the emergency spillway for the first time in the structure's operational history. Initial flow rates were relatively modest, approximately 1,000 cubic feet per second, but the psychological impact was enormous. The emergency spillway's activation represented acknowledgement that the primary flood control system had failed and that dam safety now depended on an auxiliary system with unknown performance characteristics. Emergency spillway operation initially proceeded without obvious problems. Water flowed smoothly over the concrete weir and began its descent down the natural hillside channel toward the river. However, operators and engineering staff immediately recognized that sustained operation at higher flow rates could create new failure modes that were potentially more dangerous than the main spillway crater. The emergency spillway channel consisted of natural soil and rock that had not been designed to withstand the erosive forces of high-velocity water flow. As reservoir levels continued rising, emergency spillway discharge increased proportionally, reaching approximately 12,500 cubic feet per second by February 12. This flow rate generated water velocities and erosive forces that began visibly altering the natural channel configuration. Aerial surveillance revealed progressive erosion at multiple locations along the emergency spillway channel, with particular concern focused on areas where the channel curved or encountered variations in soil conditions. The most critical vulnerability became apparent when engineers recognized that continued emergency spillway erosion could potentially undercut the concrete weir structure itself. The weir had been constructed with relatively shallow foundations, adequate for its intended function as an emergency overflow structure but not designed to withstand the foundation erosion that sustained high-flow operation might produce. Loss of the emergency spillway weir would eliminate controlled overflow, forcing uncontrolled overtopping of the dam's main embankment. Engineering calculations revealed the catastrophic potential of this failure progression. If emergency spillway erosion compromised the weir structure, reservoir levels would continue rising until water began flowing over the earthen dam embankment itself. Earthen dams are not designed to withstand overtopping flows, and such conditions typically result in rapid embankment failure and uncontrolled reservoir release. The potential failure of Oroville Dam would threaten hundreds of thousands of downstream residents with little warning time for evacuation. This analysis prompted the most difficult decision in the crisis sequence: whether to continue emergency spillway operation with its associated erosion risks, or attempt to reduce reservoir levels through renewed main spillway operation, despite the massive foundation crater. Either choice involved significant risks that could not be precisely quantified. Continued emergency spillway use might trigger progressive failure leading to dam overtopping, while renewed main spillway operation might worsen foundation conditions and eliminate future discharge options entirely. On February 12, dam safety officials made the decision to prioritize immediate reservoir level reduction over long-term spillway preservation. Main spillway operation resumed at approximately 100,000 cubic feet per second, directing flow through the damaged structure despite obvious risks of accelerating foundation erosion. This decision reflected recognition that the immediate threat of emergency spillway failure outweighed concerns about further damaging the main spillway infrastructure. The resumed main spillway operation created a surreal operational environment where massive volumes of water flowed through and around the foundation crater, generating spectacular erosion effects that were continuously monitored for signs of progressive failure. High-velocity flow scoured additional material from the crater walls and floor, creating increasingly dramatic erosion patterns that extended well beyond the original spillway boundaries. However, the concrete portions of the spillway structure that remained intact continued to channel the majority of flow toward the river, preventing complete loss of discharge capacity. Monitoring systems during this emergency operation focused intensively on detecting any change in spillway performance that might indicate imminent structural collapse. Flow measurements, visual observation, and photographic documentation were conducted continuously to track erosion progression and identify potential failure indicators. This monitoring revealed that while erosion continued, it appeared to be stabilizing as the flow encountered more competent rock layers beneath the original saprolite foundation. The emergency operation also demonstrated the limitations of existing dam safety protocols for managing infrastructure failures of this magnitude. Standard emergency procedures assumed that primary spillway systems would either function normally or fail completely, with emergency spillways providing reliable backup discharge capacity. The Oroville situation involved partial failure of the main spillway combined with questionable reliability of the emergency system, creating a scenario that existing protocols had not anticipated. Coordination between multiple agencies during the emergency revealed additional systemic vulnerabilities in dam safety management. The California Department of Water Resources, which operated the dam, required approval from federal regulators for emergency spillway modifications, but such approvals typically required engineering analyses that could not be completed within the timeframes demanded by rising reservoir levels. The regulatory framework that worked effectively for routine dam operations proved inadequate for managing rapidly evolving emergency conditions. Weather forecasting added another layer of uncertainty to stabilization efforts. Additional storm systems approaching Northern California threatened to produce inflows that would overwhelm any discharge capacity achievable through the damaged spillway systems. Operators faced the possibility that even maximum spillway discharge might be insufficient to prevent reservoir overtopping if projected storm intensities materialized. This meteorological uncertainty forced consideration of even more extreme measures, including controlled breaching of auxiliary dam structures to increase discharge capacity. The stabilization period also revealed how infrastructure failure could cascade beyond the immediate facility. Massive spillway discharges, whether through the damaged main spillway or the erosion-prone emergency spillway, created downstream flooding concerns that complicated operational decisions. Communities along the Feather River experienced unprecedented flow rates that threatened levee systems and required evacuations based on flood projections rather than dam failure scenarios. Public communication during the stabilization attempts highlighted the challenge of explaining complex engineering uncertainties to populations facing potential evacuation. Officials struggled to convey that the dam itself remained structurally sound while acknowledging that spillway failures created risks that could not be precisely quantified. The technical distinction between spillway failure and dam failure was crucial for engineering assessment, but proved difficult to communicate effectively to concerned residents. By February 13th, intensive spillway operation had succeeded in reducing reservoir levels below the emergency spillway activation point, providing temporary relief from the most immediate failure threats. However, this achievement came at the cost of further devastating the main spillway infrastructure and demonstrating that the emergency spillway could not be relied upon for sustained operation. The stabilization had been achieved, but at the cost of revealing that Oroville Dam's flood control capability had been fundamentally compromised. The emergency also exposed the vulnerability of California's water supply system to infrastructure failure. Oroville Dam represented a critical component of the state water project, and its impaired flood control capability had implications extending far beyond immediate dam safety. The spillway failures had revealed systemic risks in aging infrastructure that had been assumed to provide reliable service indefinitely. The months following the emergency revealed the full scope of infrastructure deterioration, through comprehensive forensic investigation that had never been undertaken during the spillway's operational life. Advanced geotechnical exploration, including deep drilling and ground-penetrating radar, exposed foundation conditions that contradicted every assumption upon which the spillway's design had been based. The investigation findings would fundamentally alter understanding of concrete infrastructure durability and establish new protocols for monitoring aging dam systems. Core samples extracted from the spillway foundation revealed extensive saprolite development throughout the bedrock that had been classified as competent during original construction. Geological analysis showed that chemical weathering had penetrated far deeper into the Smartville phyolite than 1960s investigation techniques could detect. In some areas, chemically altered rock extended more than 100 feet below the original spillway foundation, creating conditions where any significant water infiltration would inevitably lead to progressive erosion and structural undermining. Laboratory testing of saprolite samples demonstrated the dramatic difference between dry and saturated material properties that had not been characterized during design investigations. When dry, the saprolite exhibited compressive strengths adequate for supporting concrete structures, but when saturated and subjected to hydraulic pressure, the same material became highly erodible with virtually no resistance to particle removal. This fundamental change in material behavior under operational conditions explained how foundation failure could develop without producing obvious surface indicators until catastrophic exposure occurred. Detailed inspection of the demolished spillway structure revealed extensive deterioration throughout the concrete and drainage systems that surface inspections had failed to detect. The embedded terracotta drainage pipes showed advanced stages of chemical dissolution, with many sections completely missing and others reduced to fragments that provided no drainage capacity. Concrete core samples revealed alkali aggregate reactions, chloride penetration, and microcracking that had compromised structural integrity throughout the spillway's operational life. Chemical analysis of the eroded foundation materials provided forensic evidence of the timeline over which deterioration had been progressing. Mineral deposits and chemical signatures indicated that significant water infiltration and saprolite erosion had been occurring for at least 15 to 20 years before final failure. This extended deterioration period demonstrated that the spillway had been operating far below its design safety margins for decades, while appearing to function normally through routine inspection procedures. The forensic investigation also revealed critical design assumptions that had been invalidated by actual operational experience. The assumption that concrete bedrock interfaces would remain watertight had been contradicted by thermal cycling effects that were not fully understood in the 1960s. The assumption that embedded drainage systems would function indefinitely had been proven incorrect by chemical and sediment infiltration processes that gradually eliminated drainage capacity. The assumption that foundation bedrock would provide stable support had been invalidated by previously unrecognized geological conditions. Advanced instrumentation installed during reconstruction efforts provided data on spillway behavior that had never been available to operators during 5 decades of operation. Piezometers, measuring subsurface water pressure, revealed fluctuations that correlated with spillway discharge rates, confirming that hydraulic pressure beneath the concrete had been varying significantly during routine operations. Strain gauges embedded in new concrete sections showed stress concentrations that indicated foundation settlement and movement that had been occurring without detection. The forensic findings necessitated fundamental revisions to dam safety protocols throughout California and eventually across the United States. The Federal Energy Regulatory Commission established new requirements for comprehensive foundation investigation at existing spillway facilities, recognizing that visual inspection techniques were inadequate for detecting the types of deterioration that had caused the Oroville failure. These new protocols required periodic subsurface exploration, advanced materials testing, and instrumentation installation to monitor conditions that could not be assessed through surface observation. Engineering analysis of the failure sequence revealed systemic flaws in the approach to aging infrastructure management. The emphasis on routine maintenance of visible components had obscured the need for comprehensive assessment of hidden infrastructure elements that were critical to structural performance. The confidence in concrete permanence that had shaped maintenance philosophies for decades was replaced by recognition that all infrastructure components require continuous monitoring and eventual replacement regardless of surface appearance. The investigation also exposed regulatory gaps that had allowed critical infrastructure deterioration to progress without intervention. Existing dam safety regulations focus primarily on structural stability and flood control performance, with minimal requirements for assessing the condition of auxiliary systems like spillway drainage. The regulatory framework assumed that properly constructed concrete infrastructure would provide reliable service throughout its design life, an assumption that the Oroville failure demonstrated to be incorrect. Professional engineering practices underwent significant revision as the forensic findings were disseminated throughout the dam safety community. The traditional approach to spillway design, which emphasized hydraulic performance with structural components assumed to be permanent, was replaced by integrated design philosophies that explicitly considered infrastructure aging and deterioration over operational timeframes. New design standards required consideration of maintenance access, component replacement, and long-term monitoring as essential elements of spillway systems. The economic implications of the forensic findings extended far beyond the immediate costs of Oroville reconstruction. Analysis revealed that similar vulnerabilities likely existed at numerous other dam facilities constructed during the same era, using similar design approaches and materials. The need for comprehensive infrastructure assessment and potential reconstruction at multiple facilities represented investment requirements that had not been anticipated in long-term water management planning. Reconstruction of the Oroville spillway incorporated lessons learned from the failure investigation, but also revealed the complexity of applying new knowledge to existing infrastructure systems. The new spillway design included extensive foundation treatment, redundant drainage systems, comprehensive instrumentation, and construction techniques that address the specific failure modes identified through forensic analysis. However, integration of these improvements with existing dam infrastructure required engineering solutions that had no precedent in conventional practice. The reconstructed spillway began operation in 2019, incorporating monitoring systems that provided real-time data on foundation conditions, drainage system performance, and structural behavior. This instrumentation revealed spillway behavior characteristics that had been invisible to operators for decades, including seasonal variations in foundation pressure, thermal effects on structural performance, and the gradual evolution of concrete properties under operational loading. The data confirmed that spillway systems were far more dynamic than original design assumptions had recognized. Long-term monitoring of the reconstructed facility provided validation of forensic conclusions about the original failure mechanism. Instrumentation data showed that even with improved foundation treatment and drainage systems, spillway operations created subsurface pressure variations and material stresses that required continuous monitoring to ensure safe performance. The monitoring confirmed that spillway safety depended on active management of infrastructure condition rather than passive reliance on structural permanence. The Oroville investigation ultimately demonstrated that infrastructure failure had not resulted from negligence, inadequate maintenance, or design error within the context of 1960s engineering practice. Instead, the failure represented the inevitable consequence of operating complex infrastructure beyond the timeframes and conditions for which fundamental design assumptions remained valid. The spillway had been designed according to established engineering principles that proved inadequate for managing infrastructure aging over operational periods that exceeded the experience base of any previous facility. The systemic lesson extended beyond spillway engineering to encompass broader principles of infrastructure management in aging systems. The investigation revealed that infrastructure reliability could not be maintained through routine inspection and maintenance alone, but required comprehensive assessment of hidden components, continuous monitoring of performance parameters, and periodic reconstruction based on evolving understanding of material behavior and system performance. The forensic evidence established that the Oroville spillway failure was not an isolated incident, but rather a preview of challenges that would increasingly confront aging infrastructure systems throughout the United States. The investigation findings provided a framework for identifying and addressing similar vulnerabilities before they resulted in emergency conditions, but also revealed the magnitude of investment required to maintain infrastructure reliability in systems that had been assumed to provide permanent service. The concrete monolith at Oroville, the tallest dam in the United States, never cracked, never shifted, never came close to collapse. Its core assumptions held. Its embankment resisted the rising reservoir exactly as designed. From a distance, the structure that symbolized California's water security appeared calm, immovable, almost indifferent to the chaos unfolding around it. And yet, on February 12, 2017, nearly 180,000 people were told to leave their homes. They fled not because the dam was failing, but because the system built to protect the dam had quietly lost its authority over water. The evacuation order marked the moment when engineering certainty gave way to uncertainty, when officials could no longer guarantee that the remaining barriers between a full reservoir and downstream communities would hold. That uncertainty did not emerge from a single crack or dramatic rupture. It emerged from erosion measured in inches, hidden beneath concrete for decades, progressing without alarms, without sensors, without anyone seeing it happen. What forced the evacuation was not a flood, but the realization that water had been operating under different rules than engineers believed. For 50 years, Oroville's main spillway embodied control. Gates opened. Water flowed. Calculations held. Each successful operation reinforced confidence that the structure behaved exactly as it always had. Even as materials aged, even as drainage systems degraded, even as foundations quietly changed beneath the surface, the spillway continued to perform its visible function. It moved water downhill. That visible success concealed a deeper truth. Infrastructure does not fail when it stops working. It fails when it keeps working while its margins disappear. By the time operators saw water erupt from the spillway surface on February 7th, the system had already crossed a threshold. The tiny pathways beneath the concrete, microcracks, dissolved drains, eroded saprolite, had connected into a continuous network. Water no longer needed permission to move where it wanted. Pressure no longer dissipated where engineers intended. The spillway was still discharging water, but it was no longer governing it. The crater that emerged when flows stopped was not a sudden wound. It was an archaeological cross-section of neglected time. Each layer of eroded material recorded a season when assumptions went unchallenged. Each void beneath the slabs marked a year when drainage quietly failed. The spillway had not betrayed its designers. It had simply outlived the certainty of their premises. When the emergency spillway began flowing for the first time in history, the illusion of redundancy collapsed. What was meant to be a last resort overflow became the front line, and almost immediately, it too began to erode. Hillsides peeled back, channels deepened. Engineers watched as water started carving its own geometry into terrain that had never been hardened, never instrumented, never truly tested. That was the moment the evacuation became unavoidable. Because if erosion reached the emergency spillway weir, if water undermined that shallow foundation, there would be no spillway left at all. The next path downhill would be over the dam itself, and earthen dams do not forgive overtopping. They unravel. So officials made the call. Sirens sounded, highways filled, towns emptied, not because disaster had arrived, but because no one could say with confidence where the next inch of erosion would occur, or how fast it would propagate once it did. The evacuation was the price of epistemic failure, the cost of not knowing what was happening beneath. The surface of a system assumed to be stable. In the months that followed, forensic investigation rewrote the story of Oroville. The failure was no longer framed as an anomaly or a freak event, but as an exposure. It revealed what happens when infrastructure is treated as static in a world governed by slow chemistry, thermal cycling, sediment, and time. The spillway had been designed to control floods. It was never designed to reveal its own aging. That distinction matters, because Oroville was not unique. Its materials, drainage philosophy, foundation assumptions, and inspection regimes mirrored those of dozens of large dams built in the mid-20th century. The same confidence in concrete permanence. The same reliance on buried systems that could not be seen or maintained. The same focus on surface performance over subsurface reality. What failed at Oroville was not concrete strength or hydraulic capacity, it was visibility. The reconstruction did more than replace a spillway. It embedded a new philosophy. Foundations were overbuilt. Drainage was redundant. Instrumentation was continuous. The structure no longer merely carried water, it reported on itself. Pressure, movement, seepage, temperature, all became measurable, observable, actionable. The rebuilt spillway does not promise permanence, it promises awareness. And that is the real lesson of February 2017. Modern infrastructure cannot be trusted to remain safe simply because it has always worked. Time does not announce when it invalidates old assumptions. Water does not respect design intent, and failure does not always begin where engineers are looking. Sometimes, disaster is triggered by something almost absurdly small, a hidden erosion channel beneath concrete, expanding silently until the moment arrives when control is no longer assured. At Oroville, a tiny unseen process beneath a spillway forced 180,000 people to flee, not because the dam failed, but because certainty did. And in that evacuation lies a warning far larger than the crater itself: infrastructure that cannot be seen, cannot be monitored, and cannot be questioned will eventually decide its own terms of failure. The question is never whether water will find a way. The question is whether we will see it in time.